So in this lecture, we're going to talk about regression analysis and some of everything you've learned in the last couple of weeks. So remember our two big ideas about the linear model. First, the linear model is an equation about the relationship between the actual values and the model, right? And so we have our equation, actual value equals the model plus some error. And from that, we can calculate the error as the actual value minus the predicted value. Our second idea about the linear model is that we're interested in model fit. And by that, we mean the average individual error, not the total error. And we can calculate that as the average of the squared errors. So this is why we call the type of regression we're doing ordinary least squares regression, because we're getting the least squared errors. All right, so just to give you a formal definition for OLS, or ordinary least squares regression, it's an analysis that quantifies how the average of one variable systematically varies according to levels of another variable, right? So at this point, you already know all of the concepts to understand what this means, right? We have one variable on one hand, say grades, and on the other hand, we have, say, gender, right? So you are trying to look at how does grades vary according to gender. What we mean by levels of another variable is gender might have two categories, boys and girls. If you're talking about another quantitative variable or continuous variable, say like interest in school, then that's going to have an infinite number of levels, right? Well, realistically, it's going to be like whatever the scale is, 1 to 5. But theoretically, a continuous variable would have an infinite number of levels. So you could look at what is someone's grade for their interest level of 1.5 or their interest level of 3.5, right? So that's what we mean looking at the variation according to different levels. Okay, our regression analysis is always going to include at least two variables. Our dependent variable, which we're calling the y variable, which has to be continuous in this type of regression that we're doing, and our independent variables, which is the x variable, which can be categorical or continuous. And later on, in this lecture, actually, we're going to talk about control variables, which are also called covariates. And then later, in a few weeks, we'll talk about mediators and moderators. All right, so now we're going to put everything together so that you can understand regression as this whole big picture. First, remember that the linear model is a way of describing the relationship between actual values, the model, and the error. And let me get my laser pointer here. And so this is our equation for the error, which is just this in statistical notation, right? The error is equal to the actual value minus that predicted value. So the linear model is going to be describing a line. So here's the equation for a line, right? Beta 0 is the intercept, and beta 1 is the slope. So y is equal to beta 0, the intercept, plus the slope times whatever the x value is. Now, remember how we calculated our intercept is whenever x is 0, y is going to be equal to that intercept. So wherever x crosses the y-axis is our intercept. And here's the equation that you can use to get that intercept, right? You're just multiplying your slope by the mean of x and then adding the mean of y. You get that intercept as we calculated with this data set over here. And then for a slope, how we interpret that is for every 1 unit increase in x, so we go this way, y is going to increase or decrease whatever that slope value is. And remember, here's that equation for it. We calculate it by using the distances of each x value from the mean of x and each y value from the mean of y, multiply those together, and then divide by our squared errors for x. So we are looking for what is the change in x based on the change in y, and we can do a hypothesis test on this slope, and it's basically to tell us whether this slope is significantly different from no relationship or a flat line. So here's our 4-point data set for our students who were taking a quiz and watching TV, right? We got our equation of y equals 7.5 plus negative 0.5x. And we interpreted that as when you watch TV for 0 hours, we expect that your quiz grade is going to be a 7.5. And for the slope, for every hour that you watch TV, we expect that your quiz grade will decrease by 0.5 points. So there's our slopes and intercepts. Now that we have seen our comparison between a correlation, a t-test, and ANOVA, you know that we interpret the continuous slopes and categorical slopes slightly differently, right? In reality, there is the same idea, but just the language changes a little bit to take into account that we're using certain variables. So for a continuous x, it's going to be, like I told you, when x is 0, y is equal to whatever that intercept is. And for a 1 unit increase in x, y is increasing beta 1 units for our slope. When we get a categorical x, that's when we're going to start using our dummy variables. Remember, a dummy variable is where one group is coded 0 and the other group is coded a 1. So that means that when we have the intercept, when x is 0, all of our x's are 0, that means we're just looking at the mean of that group that is coded 0, that reference group. That's what we call the reference group, the group that's coded 0. So our intercept now is representing when x is 0. We're not taking into account the other group, we just have our reference group left over. And for our slope, we're getting a 1 unit increase in x, so that's going from group 0 to group 1. So that means that our slope is now the difference in mean between the reference group and the group that's coded 1. So basically what happens when we have these dummy variables is we change into a t-test, right? We have the mean of group 0, and then we have the difference between group 0 and group 1 as our slope. The next thing we're talking about is mean squares. So we're not just interested in the equation for the line, we also want to know how well that line fits the data. And to do that, we compare two mean squares. The first is the mean square error, which is the average distance between actual values and the predicted values. So remember how our equation is just that. Here's the actual value, here's the predicted value. We square all that and then we divide by some degrees of freedom. So we get that as our line and see how much is each point, how far is each point from our fit line here. And when we did this for our 4-point data set, we got that mean square error of 18.75. So we're comparing the mean square error to the mean square regression. And the mean square regression is the average distance between our predicted values and the mean of y. So here we don't care about the actual values, we're looking at the distance between this line, the predicted values here, and the mean of y, which is our flat line, which would say we had no relationship between x and y, right? So we're comparing these distances right here. And so when we're comparing these two mean squares, we want our mean square regression to be a lot larger than our mean square error. That would mean that this line is fitting the data much better than just some flat line would. You notice in this data set, we actually see that our mean square regression is smaller than our mean square error, right? So in that sense, this flat line is actually a better predictor of all these points than this fit line right here. You can actually see that because when we just predict the mean of y here, we actually have 2 dots that are right on that value, whereas the fit line, only 1 dot is really on that line. And so then with our mean square error and our mean square regression, we can get another number, which is f, and that's just the mean square regression divided by the mean square error, and that's one number that can summarize, you know, which one's bigger, right? If f is larger, it's above 1, then that means that your mean square regression is a lot bigger than your mean square error, right? And then we can test the significance of that f value, which tells us whether there is some significant relationship between y and all of the x's that are in our model. And then the last number that we learned about, which is the R square, and that tells us how much variance out of all the variance that's in the data has been explained by the fit line. And this is the ratio of the sum of squared errors, right, from the mean square error to the total sum of squared errors, right? So this is the top of our mean square total number right here. So this is going to give us a ratio. It's going to give us a number that's between 0 and 1, and when we multiply by 100, we get that percentage of variance. So in our data, we would say that 25% of the variance in your quiz grade is explained by how much TV you watch. All right, so now you know how to interpret all of the numbers in this output. So here's the R square that I just told you about, right? And when we looked at correlation, we saw what the relationship between this R and the R we calculate in the correlation, they're the same, right? So the R squared is just that times itself. This is only true when we have these two predictors. And then when we looked at our ANOVA, right, that gives us the different mean squares, right? So here's our mean square regression right here. And then here's our mean square error. And SPSS, they calls it the residual, and residual and error, the same thing. But we have our two mean squares over here. We have our F-test, which is just that mean square regression divided by the mean square error. And then we have a p-value associated with that F value. And then at the very bottom is where we're going to have our intercept and our slope. Our intercept is right here, the constant of 7.5. And our slope is going to be beside the name of the variable, in this case just x, negative 0.5. And then we have a p-value, a t and a p-value associated with that slope. All right, so notice we also have a p-value associated with our intercept, but you think about why might we not care about that p-value. All right, so here are all the numbers for this data set of 4 points. And you can see now that we have gone over every component that's really important. There's other things on here, but you can, those are not quite as important yet. We'll get to a few of them a little bit later. All right, so far we've talked about regression with one predictor, either a continuous X or having dummy variables in your model. But there are many reasons to have more. So what are some reasons you can think of? All right. So when we have one predictor, we call it simple regression, and when we have more than one, we call it multiple regression. That's pretty easy, right? All right, so what are the reasons we might want to have a multiple regression instead of a simple regression? One important reason is that we can reduce the possibility of type 1 errors, which are those false positive errors. If we're running multiple independent tests, like multiple t-tests, right, then we very quickly increase the possibility of getting a false positive, right? So you can see that by the time you run 10 different tests, right, your chance of getting a type 1 error is at least 40%. So that's getting pretty up there. And then if you run 100, there's 99% chance that you've got a type 1 error somewhere. All right, and you see that when we do an ANOVA, right, you have to have the Bonferroni or the Chaffee corrections for the multiple tests that you're running. Right, so running a multiple regression takes care of that because you're running all of your tests at the same time. A second reason that we might want to have more than one predictor so that we can introduce control variables, which I'll talk about in a second. And then the third reason is that we'll be able to compare the effects of different predictors, which I'll talk about last. So let's talk about control variables. So if we take a variable like achievement in school, then we want to know maybe how much time you spend on homework is related to your achievement, right? So intuitively, we might think that there's some other factors that might be, related to your achievement that aren't just about homework, right? So maybe like what grade the student is and maybe how much homework they were actually assigned, right? And we should also probably control for gender, at least at some grades, because we know that girls tend to score higher in their grades than boys do, right? So there are different ways that we could control for those things. First, we could say, okay, well, let's randomly assign some students to get more homework and some students to get less, like we could do an experiment, right? Another way to control maybe for the fact that younger kids have less homework than older kids is say, we're only going to include students who are in the 9th grade. Yeah, the last thing we do is statistically control for those variables by including them in the regression. So since those variables are not the main ones that we're interested in, we call those control variables or covariates. It's really just a naming thing though. If we did become interested in like how much homework you got or what grade you were in, we could also call those independent variables and use the same model. All right. So we have an idea about homework and achievement, and we have some control variables that we want to include. You really have to be selective about including control variables and make sure that you have chosen them well and that you've measured them well. Otherwise, you're just introducing more problems into your analysis. All right, so what are some things to think about when you're choosing control variables? So what do you already know is significantly related to your dependent variables? So things I already mentioned about achievement. We know that girls tend to score higher in achievement, right? We might know that, you know, once you go from middle school to high school, achievement tends to drop, right? So those are some of the things that you know already, so that you should probably control for. Another is you might want to think about how closely is your control variable related to your independent variable. Remember our assumptions where we talked about you don't want variables that are too closely related to your dependent variable. Well, you also don't want variables that are too closely related to each other as independent and control variables, because that's going to make it really difficult to determine what is actually causing the effect. And then the other thing is, what do researchers in your area generally control for? So this is where you have to read the literature and just sort of see, okay, well, everyone's controlling for gender and grade, so I'll just throw those in there too. Even if you don't necessarily have a strong rationale for it, you might get questions if you don't include those in there. All right, so when we have control variables in our regression, what we do is now we can say that we are interpreting the slope for our independent variable, controlling for the other variables, or holding the other predictors constant is another thing to say. They're constant now. All right, so if we have control variables, that means that we are statistically taking into account those influences, but it doesn't mean that we actually eliminated the influence of something, right? So even if we're controlling for what grade the student is when we're looking at the relationship between achievement and homework, that doesn't mean we actually have changed anything about the students' real lives, right? We're just still just looking at data. And there might be some influence that the that effect is, that the control variable is having in the real world, that we haven't been able to measure in our analysis. And then the other thing is that it doesn't mean that our findings are representative or generalizable, right? So if you are doing your study at a very elite prep school where you have a ton of homework, right, and everyone's super high achieving, your analysis might not fit. Even though the data is really perfect and beautiful, your analysis may not fit kids who are maybe in a, you know, more traditional public high school where they don't have as much homework, or the kids aren't as achieving as very well. So control variables are really mainly about your model, and it depends on how you've measured them and what the what you think the effects might be. So then our third reason to include other variables in your model is that you can compare the two effects, or three effects, or however many you are. All right, so let's look at these slope values for easting and depth here. So this is just for an analysis looking at, I think, houses and how they're built or something like that, right? So if you just look at these two numbers, can you tell which one has a bigger effect on northing? Not really, because they're on different scales, right? But we can directly compare them if we want to by looking at these standardized beta values. Can you think of maybe why? The hint is because they're standardized, right? When they're standard, that means that they're divided by the standard deviation of y after being multiplied by their own standard deviation. So remember how we standardize when we're looking at correlation? It's a similar process when we're looking at our slope values. We can standardize those as well. Once they are standardized, then we can directly compare these two and say that depth has a stronger effect on northing than easting does. So that's a useful thing. If you wanted to go back to our homework analysis, you could think about, okay, well, I want to see if homework has a significant effect on achievement. But you could also compare and say, okay, is homework a bigger predictor, or is gender a bigger predictor of achievement? And you might be able to say, okay, well, even though we know that both gender and homework are significantly associated with achievement, the bigger effect is homework. And that can be really theoretically meaningful. All right, so just to summarize, when we're looking at simple regression and multiple regressions, a lot of things are going to be the same. The assumptions that we went over, the 4-line assumptions, are going to be the same. And the interpretation of the R-squared, the F-test, and the T-test are going to be the same. What's different? That equation, right? So for both, we're looking at this actual value equals the model plus error. But in simple regression, we only have our one x value. But in multiple regression, we end up having multiple x values. However many you have, you're going to have a slope and x for each. You're going to have a slope for each x value. Right? Still only going to have one intercept, and that intercept is going to be when all of the x's are 0. Right? So that gets to how the intercept and the slope are slightly different interpretations, right? The intercept is actually the same when all the x's, instead of just when one x is 0, when all of the x's are 0, you're going to have an intercept of beta 0. And then for the slope, the change is that it's a 1-unit increase controlling for all the other x's, right? So now we can say this is how much your achievement increases for every 1-unit increase in homework that you have every 1 hour or so, controlling for your gender, say. And then finally, here's just a summary of looking at a multiple regression, the output. And then here's the summary of how to interpret everything from the steps in data analysis, right? So in this particular analysis, we're looking at the relationship between gender, grades, and stereotyping, and how much students perceive their races being stereotyped on interest in school. So for this, we're going to start with interpreting the overall model. So we look at that F value. Remember, the F is the ratio of the mean square regression to the mean square error. And notice in Stata, our mean square regression is the mean square model, and our mean square error is the residual, like in SPSS. So this is F value is going to be this divided by this. So we get a 54.48. So we can say that is bigger than 1, so that means that our mean square regression is a lot bigger than our mean square error. That's what we want. And then we also have a p-value associated with that F value. So this means that our overall model is statistically significant, right? So that these X predictors are giving us more information about our data than just a flat line that would be at the mean of interest. Next, we can interpret our R-squared value, and this is the percent of variation in interest that's explained by the variation in the predictors. So our R-squared value is 1.1672, so we would say 16.72% of the variation in interest is explained by these 3 predictors. Great. Now, the amount of variation that will be explained will depend a lot on your field, right? So in education, we're usually used to having very small prediction, right? Because things like grades, interest, all those things are going to be explained by a lot of different variables, right? And so having 16% is actually really good here. But if you're looking at data where you might have more information about what's going into everything, you might have a bigger R-square. And that's okay. It's just kind of looking at what your field is and determining what's a good R-square. There's our R-square. And next, we're going to interpret our intercept, right? So when all of the x's are 0, y is equal to beta 0. All right, so in Stata, our intercept is down here at the bottom. So when all of these x's are 0, gender is 0, grades is 0, stereotyping is 0, and we can expect our mean to be 4.13. Okay, now notice we have gender in here. That is in fact a dummy variable where boys are 0 and girls are 1. So in this case, what we're seeing here is that if everything is 0, then this mean is going to be for boys, right? These are boys who scored 0 in grades and 0 on stereotyping, and their mean would be a 4.13. Now keep in mind that our intercept is not always interpretable, right? In this case, grades and stereotyping are both on 1 to 5 scale, so a 0 for those doesn't really make a lot of sense. So this intercept right here is not really all that helpful to interpret, but that's what it means if you wanted to interpret them. Now, for interpreting our slopes, remember for our continuous slopes, we got a 1 unit increase in x, y increases, beta 1 units controlling for the other x's. So which ones of these are continuous, right? Grades and stereotyping. So for grades, we would interpret this as a 1 unit increase in grades is associated with a 0.54 decrease in interest, right? So that's interesting. And we're seeing that students who get higher grades are actually less interested in school. I don't know, maybe they're bored, maybe they find things too exciting there. And this is controlling for the other x's. And for stereotyping, it'd be a similar thing. For students who go a 1 unit increase in stereotyping, we have a 0.12 increase in interest. So these students actually, when they feel like they're being stereotyped, they're more interested in school. Maybe they have this feeling like I need to prove them wrong, so I'm gonna, become more interested in school and work harder. So that's kind of an interesting idea there, interesting finding. And then for our categorical slope, what we're doing is looking at controlling for the other x's. The group coded 1 is on average beta 1 higher than the reference group, right? So remember how we got our mean for the boys when these are 0 as 4.13. The girls are going to be 0.21 higher than that when these are controlling for these, right? When these are 0. So we can see now that if you go from a 0 for boys to a 1 for girls, then girls are going to be higher on interest than boys. And we can look at the t-test for each of these slopes. In all of these cases, the slopes are, the p-values are below 0.05. So we say each of these slopes, each of these x variables is significantly related to interest. And then what we can also do is compare, if we include our beta values, we can compare the size of each effects to each other, right? So in this case, we're just looking for the largest absolute value, right? Since grades is negative, the beta value is also going to be negative, but we're really just looking for the largest one. And in this case, we can see that grades has the biggest effect on interest in this analysis, and gender and stereotyping have relatively smaller effects on interest compared to grades. So even though all of them were significant, we can see that grades is having that larger effect. All right, and then if we had a hypothesis here, we would check to see was our hypothesis supported. And when you're checking to see that our hypothesis is supported, you gotta make sure that you're looking at both the sign of the effect as well as whether it's significant or not. So if we had predicted that grades would be associated with higher interest, higher grades are associated with higher interest, right, then this would actually, even though it's significant, it would not support our hypothesis because we're seeing that higher grades is associated with lower interest. So you gotta double check that your hypothesis, both the sign and the significance, is matching what your actual data is showing you. So that's the interpretation. All right, and then here's our code for actually running a regression in Stata and SPSS. Stata makes it nice and easy because it has basically all of these kind of built in and some things you have to do afterward. But what this is going to give you, if you do it with the comma beta at the end, that's going to give you those standardized coefficients. In SPSS, we're asking for all of our values here, dependent and independent variables. And then this last part here is asking for the residual analysis, which we're going to talk about in the next video.